Hey there, and welcome to This Explainer. I am absolutely thrilled to take you on a wild journey today. Seriously, I want you to imagine stepping into a theoretical time machine with me right now. We're going on a massive cosmic road trip to a time where our universe is going to look and act completely differently. I'm talking dead stars, raining black holes, and an Earth that is nothing more than a distant memory.
The universe is 13.8 billion years old, vast, ancient, and mostly invisible. And somewhere out there are answers to questions that keep scientists awake at night. Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
So, let's just dive right in with the ultimate existential question, shall we? Can humanity actually survive 10 quintillion years into the future? It's a staggering, almost impossible thought. The astronomical odds stacked against us are, frankly, mind-bending. But before we start jumping through the timeline to see exactly what tries to wipe us out, we really need to wrap our heads around exactly how far into the future we're talking about. I want to anchor you to the sheer, unbelievable scale of this. 10 billion billions. That is a 1 followed by 19 zeros. It is a completely unfathomable amount of time. But, to understand the end of the entire universe, we kind of have to start a little closer to home. Okay, Section 1, the Near Future Crises. Let's set our time machine for just 1 billion years from today, where the changes happening to our own home planet are going to be absolutely terrifying. In just a billion years, our beautiful blue marble? Yeah, it's a dull brown rock. Why? Well, because the sun is growing hotter, about 1 degree Celsius every 100 million years. This pushes Earth's average surface temperature to a scorching 47 degrees Celsius or 117 degrees Fahrenheit. This intense, unrelenting heat totally disrupts the carbon cycle, which kills off plants and animals. Eventually, all of our oceans literally just evaporate. Earth becomes a dry, dead rock. So where are we during all this? Hopefully, we've packed up and migrated. Mars wouldn't even be safe at that point. We'd need to go much, much further, or perhaps even upload our consciousness in a machine so we can live virtually forever. But here's the catch with that. Whether we're powering off-world colonies across the galaxy or running massive mainframes for virtual realities, we are going to need immense amounts of energy. And this brilliantly illustrates a major roadblock we face right now. Solar panels, they generate direct current, or DC electricity. But our future buildings and power grids, they require alternating current, or AC electricity. Converting one to the other requires an inverter, and right now, we literally lose energy in that process. To evolve into this advanced, galaxy-spanning civilization, we absolutely have to solve this energy conversion inefficiency today. And that brings us to a massively important number, 99.7. That is the efficiency percentage of the zero-voltage switching, or ZVS inverter, which is actually being developed right now by Hillcrest Energy Technologies. Operating at 99.7% efficiency drastically reduces energy loss. I mean, this kind of tech can reduce electric vehicle battery pack sizes by up to 15%, saving thousands of dollars. And it has massive applications for data centers and grid systems. It's exactly this kind of active, innovative problem solving that's going to power our future colonies. So, now that we've got our future energy needs sorted out, let's map out the next leg of this journey. We've passed the 1 billion year mark, where Earth unfortunately dies. Now we're accelerating toward the 10 billion year mark, where our sun transforms. And then we're bracing ourselves for a massive theoretical threat at the 22 billion year mark. Let's zip to 10 billion years and see what's happening. Boom! Welcome to 10 billion years in the future. By now, our sun has burned through all its fuel, expanded into a red giant, which completely vaporized Earth, by the way, and then collapsed into a dim white dwarf about the size of Earth. But the much bigger news here is the Milky-Meter merger. Our Milky Way is colliding with the Andromeda Galaxy at a blistering 400 million kilometers per hour. If you were standing in the middle of it, it would feel like a violently shaken snow globe. But instead of snow, it's massive rocks, planets, and stars. Now, the vast distances mean stars probably won't physically crash into each other, but gravitationally, oh, it is total chaos. There's a 50% chance our dead solar system gets pushed 3 times further away from the core, and a 12% chance it gets ejected completely into deep space. We had better be living in a different galaxy by then, for sure. Let's skip ahead to 22 billion years. things are getting super complicated because of something physicists don't even fully understand yet: dark energy. Dark energy is causing the universe to expand faster and faster, which could actually lead to something called the Big Rip. This is a working theory where the expansion accelerates so violently that star systems, planets, and eventually individual atoms themselves literally tear apart and dissolve. It is a terrifying potential end to everything. But just for the sake of our journey today, let's assume we somehow dodge the Big Rip and keep going. Moving right along into Section 2, the end of the Stelliferous era. Fast forward with me past the threat of the Big Rip, all the way to 100 trillion years in the future. We've reached a monumental transition point. The universe is literally about to run out of its most basic raw materials. At this point, our once vibrant universe has essentially become a cooling star graveyard. For trillions of years, giant clouds of interstellar hydrogen gas birthed brand new stars. But not all the mass from dying stars gets recycled, you know? Eventually, that raw hydrogen just runs out completely. So what's left? Well, small, dim red dwarfs that live for 80 to 100 billion years finally die out. Failed stars, known as brown dwarfs, cool down to a mellow 2,500 degrees Celsius. And the massive stars? They've long since gone supernova, leaving behind ultra-dense neutron stars or black holes. One by one, the lights are turning off across the entire universe. And wow, here we are. 10 quintillion years. This marks the degenerate era. And no, as the original source so cleverly points out, that is not an era where a bunch of Redditors take over the universe. It just means the universe is a dim graveyard littered with dead stellar remnants. The only real action happening is the incredibly rare collision between two dead stars, which might briefly spark a supernova or a new star before plunging right back into the cold dark. Let's push that time machine even further. Imagine a 1 followed by 34 zeros. That is 1 decillion years. The universe at this stage is incredibly bleak. It's getting cooler, it's getting darker, and something fundamentally foundational is about to break down entirely. We are now witnessing the literal death of matter itself through something called proton decay. This is the incredibly slow process where the tiniest subatomic particles, the very building blocks of matter, just begin to disintegrate and die. Because of this decay, those few glowing remnants, like white dwarfs, will fade away until they have the brightness of just a few household light bulbs. The physical fate of the universe is pretty much being sealed right here. Which brings us to an unfathomable 1 with 40 zeros, 10 duodecillion years. Welcome to the black hole era. At this point in time, there are no planets, no shining stars, no dwarfs left. The only things producing even a very weak shine are black holes. They're acting like massive planetary zombies, just scarfing up the decaying remnants of dead stars, becoming denser and even more massive. You might think they are completely unstoppable, but it turns out even they have an expiration date. Let's break down exactly how a black hole dies. You thought Thanos was bad? Nothing escapes a black hole, right? Well, actually, scratch that. Hawking radiation does. First, twin particles spontaneously appear right at the mouth of a black hole. Then, one particle falls in, but the other one actually escapes. Because of this weird quantum loophole, the black hole slowly leaks tiny bits of radiation and loses mass. And finally, over trillions upon trillions of years, this steady leakage causes even the most massive black holes to simply evaporate and die. So what on Earth, or rather, what in the universe is left when the very last black hole evaporates? Let's push our time machine to the absolute extreme for our final major stop. Section 3, the final dark freeze. A Google years into the future. That's a 1 followed by 100 zeros. Welcome to the dark era. It is cold, it is dark, and it is very, very quiet. The sadness of this era is honestly profound. The universe has expanded so incredibly much due to dark energy that the few remaining subatomic particles left are unimaginably far apart. You would literally have to zip all over the entire footprint of our current universe in your time machine just to catch sight of a single, lonely subatomic particle. So ultimately, how does the whole story end? It really comes down to two potential fates. The Big Freeze is an infinite expansion driven by that relentless dark energy, stretching and distributing all energy evenly until the temperature of the universe is just a hair above absolute zero, way colder than a winter in Canada. The alternative is the Big Crunch, where the expansion suddenly switches into reverse, contracting everything back down to a single tiny cell, potentially starting a brand new Big Bang. While a bouncing, recycling universe sounds pretty poetic, scientists currently believe that dark energy has the upper hand, making the big freeze the much more likely scenario. Let's bring this massive, mind-bending cosmic narrative back down to the human element for a second. How do we survive in a universe with absolutely no stars? We need luminous stars to create habitable zones and grow food, right? If the universe goes completely dark and freezes over, are we just doomed? Well, think about these evolving survival strategies. Keep in mind, we are only about 200 years past the Industrial Revolution. Think about what we could do in centuries, let alone quintillions of years. We might completely shed our physical bodies and exist entirely in the form of pure energy. We'll likely progress from a Type 1 civilization all the way to a Type 7, using our immense evolved intelligence to manipulate the very fabric of our environment. Or, perhaps most mind-boggling of all, we might just figure out how to build an entirely new universe for ourselves inside a laboratory. Which leaves us with one final, completely wild, provocative thought. If we can manipulate energy to that degree, and if we can literally build a universe in a lab to escape the big freeze, will humanity be the ones to spark the next Big Bang? Will our incredibly distant descendants cease being mere inhabitants of the universe and instead become the creators of the next cosmic cycle? It is an absolutely fascinating question to ponder. Thank you so much for joining me on this explainer through space and time. Keep wondering, and I'll catch you next time.
The universe doesn't care about us. It never did. But we care about it. And that is what makes us extraordinary. If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.